I'm really happy to be here. I spent, I'm sorry, very good. Thanks, Scott, I forgot that. I spent a wonderful time here, and I can't really think of being here without Willy, so I'm also a bit sad to be here at the same time. It's really a bit touching. It may be different for some of you who are usually living here, so they are used to him not being around, but I come from Europe, and for me, it's really not so simple. I mean, I miss him a lot. And so before the batteries are done, let me quickly say a little bit about myself. So I started my PhD in '91 in the group of Erhard Steffens and Dieter Fick in Heidelberg. And soon I realized that there was occasionally an older person coming in who would ask seemingly simple questions, which were troubling all of us a bit. And it turned out that this was Willy. He was in Germany at that time on a scholarship from the Humboldt Foundation. And he was working on this experiment with us. And since that time, say since '91, I interacted with Willy. Later on, I joined Hans's group, or Hans and Willy's group, as a postdoc, the Pintex collaboration that was mentioned before. And we worked together until the end of the Kula at IUCF. I moved back to Germany in '97 already to start in Jülich at the Kula synchrotron in Jülich. And this particular experiment, or these studies I'll talk about here, basically developed, say, after 2010, I would say. And at that time, I didn't have that much interaction with Willy anymore. But I must say all the techniques, all the inspiration for this type of research is, I mean, it's basically his legacy also on me. I mean, I'm of course one of his last postdocs. I'm not sure whether I'm the last one, but it could well be that this is the case. Okay. So this is about the first direct electric dipole moment measurement with deuterons at COSY. At the very end, I have a realistic strategy presentation to tell you a little bit about how one would go from here to a dedicated EDM ring with ultimate precision, which would be, say, could be a future for nuclear physics in doing fundamental symmetries. So this thing should now switch. No. No, it's down is fine. Down is also not fine. And up is certainly not working.
There's nothing up.
Yeah. So the only thing that works is the pointer, which is already good. Okay, so can you just put please on the next slide?
Yes. Oh, actually, try again. Not working?
No. You did that or did I do that? Did you switch it now or did I?
I did.
Very good. Okay, so this is the contents. I have a brief introduction here. I have some progress which we did, where actually Ed Stevenson played a major role in all these developments with us in that collaboration that we currently have. I'll talk in technical detail about the first deuteron measurement at COSY. We don't have a final result yet. Briefly touch the future and give an outline of the give a summary. Very good. So the problem somehow is that we have this baryon asymmetry in the universe. We know, that observation and expectation from the standard cosmological model is very different. So the observations of the number of baryons minus the number of antibaryons divided by the number of relic photons is a number which one can measure. And these two experiments here measured that the number is about 6 × 10⁻⁻10. And the expectation from the standard cosmological model, which kind of combines what we know about cosmology and the standard model, is on the order of 10⁻18. So the standard cosmological model really gets it wrong by more than 8 orders of magnitude. And can you please go to the next slide? Okay, very good. And so the question is, what does this have to do with electric dipole moments? So apparently we are looking for something that violates parity and time reversal. And you can go through this derivation here, but it's maybe easier to see this in the cartoon here. If you have an object that has an electric dipole moment d and a magnetic moment mu, and you apply parity operation, you end up with a different object. And if you do time reversal, you end also up with a different object. So it means EDMs, electric dipole moments, violate both P and T, and they could constitute the missing cornerstone to explain really that CP violation in the early universe. Of course, the books would have to be rewritten because it would add a fourth quantum number to fundamental particles. Okay, one can have a naive estimate of the scale of the nucleon EDM, which was derived by Kripolovich and Lamoureux and later on by Nikolaev. So one can start out with a CP and P conserving magnetic moment, which is equivalent to an EDM of say to a magnetic moment of about 10 to minus 14 e centimeter. If you want to see a non-zero EDM, you have to pay a price in terms of parity violation, which is 10 to minus 7. And CP violation in the standard model, which is another factor of 1,000. So that means, in summary, the EDMs could start to show up about at that level. And in the standard model, without the theta QCD term, the lower limit is kind of given then by about 10 to minus 31 e centimeters. So the window to search for beyond standard model physics is about between 10 to minus 24 to 10 to minus 31 e centimeter. The direct measurement of the neutron, which we currently have from the PSI experiment in Switzerland, is on the order of 10 to minus 26. So there is still a window to learn about, but this is the only direct measurement. So what you see here are the currently known EDM limits. In fact, here the only measured hadron, which is the neutron from that PSI experiment on the order of 10 to minus 26. We don't have direct EDM measurements. We have no direct EDM limit from the electron. The limit is obtained from thorium oxide. We have no limit from the proton, from mercury. We have no measurement of the deuteron. And to summarize the theories around electric dipole moments, anyway, it will not be sufficient. Once you find a limit, it will not be sufficient to identify the CP violating source from a single particle. So you will need other sources like protons, neutrons, helions, deuterons, and other particles to really pin down where it comes from. So let me quickly speak a little bit about spin precession. I mean, Thomas Rosa already mentioned that briefly. So in the rest frame of a particle, this is what a spin vector S is doing in a magnetic field B and an electric field D when the electric dipole moment is D. If you put, for instance, protons in a storage ring, the spin precession is governed by the Thomas BMT equation. And this is just given here. So you can actually make the omega MDM precession minus the cyclotron precession vanish by making this omega equal 0. And you can do that for particles which have actually a positive G factor by making this, by setting this piece here 0 in the absence of magnetic fields. And this means at a momentum of about 700 MeV over C, protons in a ring don't precess anymore. Thank you. So the recipe basically for an EDM measurement in a purely electrically deflecting machine is you put the particles in the ring, you align the spin along the direction of flight. That is, you freeze the horizontal spin precession. You search for the development of a vertical polarization out of plane by this D cross E term. And this is your signal for an EDM. So that means you can build rings, magic rings with a frozen spin along, and the polarization built up is proportional to the electric dipole moment. Now, that actually, there's different ways how one can do that for particles which don't have a positive G factor. Yeah, negative G factors like the deuteron and the helion, you have to add a magnetic field You can add a vertical magnetic field, and then you find other solutions for such a machine. And this table here just shows for a radius of 25 meters, which E and B fields you have to fulfill in order to be able to do frozen spin in one and the same machine. So the beauty of this would be that one would have a single machine and you could do protons, deuterons, helions in principle if you manage to generate these electric fields. That's of course just for 25 meters. If you make it correspondingly larger, the E field goes down. So the experimental requirements can be put together in form of a single equation down here. So you need a certain number of particles, polarization, you need electric fields, you need something that's called spin coherence time. I come to that. You need an analyzing power and a high efficient detector. And if you insert this into this equation here, then this set produces a statistical uncertainty of an electric dipole moment of about 10 to minus 29 e-centimeter in 1 year. Of course, this is not the systematics, but the goal would be actually to provide systematics on a similar level. Great. No, previous one, please. So this is just what, say, the little progress report about what we've been doing in Jülich. This picture here shows the cooler synchrotron, which is a cooler and storage ring with momenta between 0.3 and 3.7 GeV. Obviously, no, not yet. Sorry. And it allows phase-based cooling, actually electron cooling and stochastic cooling. And until 2010, it was used mainly for spin physics and hadrons, with hadrons. And it was for us really an ideal starting point to start this storage ring EDM research and to use it as a machine for a first direct deuteron EDM measurement. I should,
You can advance on the right.
Sehr good, apparently. That.
This is a laser.
Very good. Of course, the source that drives this is a cesium charge exchange source built by Bonn, Cologne, and Erlangen. The source that Tom Clegg talked about yesterday, and so it's this thing is still up and running and does the job. So very good. So the landscape or the stuff we've been using is like COSI has about 183 meters circumference. We've been using various detector systems, snakes, an RF filter, a detector. Injection comes in here, so that's just to show the landscape. Let me discuss a little bit the principle of the spin coherence time measurement. So essentially, we inject the beam vertically polarized, and then we flip it into the horizontal plane with an RF solenoid that is on for a couple of 200 milliseconds. And then we basically have this ensemble in the machine, which is freely precessing. And basically the polarization is then measured on a carbon target, which is either put actively into the beam, or we heat up the beam so that the protons, deuterons interact with the target. And in the detector system, we can then measure the in-plane polarization from the up-down asymmetry. So we've been using the EDA detector in the beginning. Today we have a more modern detector, but to explain the principle, that's fine. So we built 4 quadrants. Out of that, the spin, say the up-down asymmetry, is actually modulated by the spin tune. And so the spin precession frequency is typical about 120 kilohertz, and the revolution frequency is about 700 kilohertz for the experiment conditions which we typically have. And of course, I just wanted to explain a bit what I mean with spin coherence. So you inject the particles, there's an axis around which the spin vectors precess, and the ensemble is coherent at the beginning, and after some time it decoheres. Most polarization experiments that use a projection, that use the projection on the stable axis, wouldn't really care about coherence. But in the case of these EDM experiments, where you actually have frozen spin, where the spin vectors are perpendicular to this precession axis, it matters, because when the spins are aligned originally, things are fine, but if the spins all get out of phase, you have no polarization left in the plane, and therefore the in-plane polarization vanishes, and therefore your polarization build-up process that gives you the sensitivity to the EDM simply vanishes. So you have to make the spin coherence time large to be able to see that polarization build-up for as long as you can. Okay, so when we started this year, I remember calculations by Alfredo Luzio from Brookhaven, who calculated that the spin coherence time at COSY would be milliseconds. And nevertheless, the group was not really affected by this adverse statement. And then we just started, and it turned out that for deuterons, tuning 6-to-pole families in the machine, it turned out that you can really achieve thousands of seconds. So routinely today, we can have like 1,500 to 2,000 seconds spin coherence time. And this is just fantastic. So you have basically 10 to 9 deuterons stored in the machine, all orbiting and precessing in the same sync. This was actually one of the main obstacles for the storage ring EDM experiments, and the statistical uncertainty is inversely proportional to the spin coherence time. So the longer you make it, the smaller your error gets in the end. A second thing that we were developing in context of that is the determination of the spin tune. Of course, this is intimately linked to the spin coherence time as well. So the issue actually is that we have the 120 kilohertz precession frequency, but in the detector you have only maybe a 5 kilohertz rate. So how do you measure something that precesses that fast? And the tool is timestamping. So you timestamp every event and project it into a single spin phase if you want. And then you can just maybe either do a fit or a Fourier transform, map it and Fourier transform and find the proper spin tune. And this is indicated here. So the actual precise how much? I'm okay. Are you listening? Okay, very good. So the actual precise determination is outlined here. So to make that story short, we monitor the phase as function of time. The analysis is assuming a fixed spin tune, and then you can basically fit the phase dependence as function of the turn number. And it turns out that we can measure the spin tune to 10 to 8 in about 10 to minus 8 in 2 seconds. And at the middle here in this 100-second cycle in this PRL, which we published in 2016, I think you see that the relative error is about 10 to minus 10. So we really have a precision tool to study, say, systematic effects in a storage ring, which we get in conjunction with this spin coherence time as well. This shows just illustrates that this is the walk of the spin tune for different fields: polarization up, polarization down. Unpolarized cycles are of course not shown here. So this shows that these bands really, the variation is much larger than the actual accuracy which we have in such a machine. So that allows one to look at long-term stability in an accelerator. You can also stabilize the phase of the spin precession using this technique. And you can, of course, study machine imperfections. So at COSY, of course, since it's a magnetic machine, we cannot freeze the spin. So you can do that. So the next best thing you can do is you can phase lock the spin precession. That means you adjust, you fix the phase between the spin precession and some device RF, either a Wien filter or a solenoid or the COSY RF. This example here is where the feedback was done with the COSY RF. So you can see here when the feedback is off, the phase is running. When the feedback is on, we can stabilize the phase nicely, and you can see that the frequency corrections necessary to stabilize that are in the order here of about 0.1 hertz, so quite accurate. The uncertainty of the phase log is was about 0.2 radian. Very good. So now let me talk a little bit about this first direct experiment. Of course, the ultimate goal would be to have an electrostatic machine where you don't have magnetic fields. Magnetic fields here for these types of measurements are actually really evil. You don't want any of them around because the magnetic moment is so much larger than the electric dipole moment. So the idea came up to come up or say to come up with an idea to show that one can use such an experiment in a storage ring, we were clear that we needed some RF technique to actually accumulate the signal. So an RF device like an RF Wien filter with E cross B fields that would allow us to phase lock the spin precession and the device RF and to accumulate the signal. And to first of all show that a conventional storage ring can already be used to do something. I mean, I would say this saved maybe COSI's life for the last 6-7 years, I would say, this experiment. Okay, so this is again about the technique. So you have a Lorentz force which you'd like to minimize with that Wien filter. You have a vertical B field and a radial E field which couples to the motional electric field of the in the ring. And you can accumulate that signal. The anticipated statistical sensitivity is about 10 to minus 23, 24, but of course, it's a magnetic machine. You have magnetic imperfections and imperfections of the Wien filter, so the real sensitivity is much less. Let me talk a little bit about the effect that an EDM has on the stable spin axis. In an ideal machine, yeah, the spins precess only about the vertical axis. Okay, now as soon as you switch an EDM on, the stable spin axis is tilted sideways. And that means you get a vertical polarization oscillation that comes from the EDM. If you don't do anything, this amplitude here is like 10 to minus 6, so you can't really do much with that. So you have to find a way to actually enhance that. And this is where the Wien filter comes in. When you basically are in sync with this oscillation, you can make that build up. And that's indicated here. So that's a model calculation with ideal COSI and the operation of the Wien filter. And you can see that without an EDM, these lines would all be flat. And now you have this fast 120 kilohertz precession and a slow polarization build-up. And if you follow this for a longer time, then you should be able to see full oscillations of the vertical polarization due to the electric dipole moment, depending, of course, on other parameters. So we've actually aimed for that, because that would, if you can do that here, that would mean the EDM resonance strength would become a frequency measurement. And as we all know, frequencies can be measured with high precision. And so this was actually the long-term goal of that. Okay, so a little bit about the Wien filter. This was a joint development by RWTH Aachen and Jülich. The idea for that, I think we cooked up between 2010 and 2012, 13. Then we found a PhD student. With him, we realized that. And by 2017, we had this device, which you can see here is about 1 meter long. One of the features is that it's rotatable in situ around the beam axis. So you don't have to break the vacuum. And of course, this allows easy changes of the Wien filter angle, which is a fantastic tool, as you will see in a moment. This is a view along the beam direction on the field plates. So by design here, we don't have two systems for E and B. It's a single system. So it produces E horizontally between the plates, and since it's RF, it also produces B vertically at the same time. It's a waveguide. Yeah, so that has the advantage that you don't have to worry about how E and B are relatively oriented, because it's hard. If you want hard, it's in the design. It's part of the design. Then we got the idea, okay, it would be real nice if we could switch the power on and off at will. So in the most recent run, we developed fast switches, which have really fantastic switch on and off characteristics. Each of them is capable to handle about 200 watts. So that was sufficient for our purpose. And the reason for that was that we wanted to have actually a form of comagnetometry. So we wanted to see what's happening in the ring when the Wien filter was off during the experiment. And we did it in the following way, that we had two bunches in the machine orbiting. And one of the bunches is the signal bunch, and the other bunch is the pilot bunch. And the pilot bunch is generated by these fast switches where the RF power of the Wien filter is switched off. So with the signal bunch, Wien filter on, you can actually see here these nice vertical polarization oscillations. And with the not affected pilot bunch, you basically see what's going on in the ring without the Wien filter. So you can simultaneously see what is happening in the machine without the RF on of the Wien filter. This shows the recent result from the data analysis. So it's absolutely beautiful. So we have one bunch with the RF Wien filter off. This is that blue line here, that blue trace. And the second bunch simultaneously orbiting in the beam sees the Wien filter on. So this is just fantastic. So I think it allows individual spin manipulation of a bunch in the machine after it was injected. So this may have implications for other storage ring experiments where you would like to say rotate the polarization of an individual bunch, say in RIG, into some other direction for systematic reasons. So this is really something that we would like to publish soon, but we're not there yet. The analysis is done by Jamal. He's the student who did PhD student who built the Wien filter. Okay, now let me quickly come here to the end, to the EDM resonance strength. So generally, the induced polarization by the EDM is a vertical oscillation of the polarization with a certain frequency and a certain phase, if you want. And if you divide the EDM, this polarization oscillation by the revolution frequency, you get something which is called a resonance strength. Yeah, and now I show you how we actually do the measurement. We apply two features in the ring. First of all, we can rotate the RF Wien filter magnetic axis by a small angle so that we can vary essentially the radial B field and affect the this polarization oscillation. Or we can add we have a little magnetic field on the opposite side, a longitudinal magnetic field, a weak one actually from Siberian snake, but run at small field. And that rotates the spin as well. And now what you would expect here is such a like coffee filter type structure where this axis is the Wien filter angle and this axis is the solenoid rotation angle. And if there were no EDM and the ring were ideal, then this is actually the orientation of the stable spin axis at the Wien filter location. Now, an EDM in an ideal ring would show up as a displacement along the Wien filter axis. Okay, so that is the signal. So basically, what we would like to see, we would like to have such a map measurement and deduce the minimum of this, and from this actually understand the EDM of the machine, or the EDM limit of the experiment. Okay, now this I show you is from the second run we did. Here you have a signal and the pilot bunch. This is now essentially the EDM effect. So the signal bunch makes nice vertical oscillations and the pilot bunch doesn't do anything. You can also nicely see here the decoherence of the ensemble. So the amplitude decreases as function of time. So the system gets sees some decoherence. You also see no oscillations in the pilot bunch. You determine the frequency of this oscillation divided by the revolution frequency, and you have your EDM resonance strength. I should say that this technique with the pilot bunch actually for us experimentally meant that we can extend the observation time. The feedback system that we were previously using would allow us to look at the spin tune and to feedback on the phase, but when you are at the maximum and the spins py are up, you can't have any feedback anymore because there's no signal in the horizontal plane. So that means we couldn't do more than a quarter build up. And so this technique now allows you to go as long as the spin coherence time warrants. So it's for the EDM experiments, I think this is also a breakthrough. Okay, now this is a preliminary result. You see here these individual points on this map, and the analysis of the minimum is given here, where these are two numbers in milliradian. We don't quite understand the spin dynamics so that we can actually have a calculated prediction where this large number comes from. So the technique, or the experiment would work, or the extraction of the result would work like that. Now you have the determination here of the minimum. You do a spin tracking in the cozy lattice and determine the orientation of the stable spin axis without the EDM. And then you take the difference between this minimum here and that calculation of 2, and this is then your EDM result. But of course, you need to be able to do a realistic spin tracking calculation of the cozy lattice. And up to now, we are working on that, but we haven't fully succeeded with that. It's complicated because of the understanding of this magnetic environment of dipole magnets and field imperfections is anything but trivial. I mean, it's a hard experiment in cozy, but as soon as you go to an electrostatic environment with shielding, these issues become smaller and you can, of course, go to a lower level. Okay, let me quickly outline the strategy. So we've been, we are in stage 1 currently doing this precursor experiment. The data are in the box. We are doing systematic studies to better understand it and to come up with an EDM limit. The CPM collaboration has actually published a CERN Yellow report. This is like a 280-page document which you can look at with all the gory details that we learned. And the conclusion is for us that to jump from here to the Holy Grail final ring is a giant step which is too large. So what we think what is necessary is to build a smaller machine, maybe 100 meter circumference, to study the remaining issues and say with a moderate EDM limit, do that next step to be safe for the future. Now let me detail this a little bit. So basically we are together with CERN and JEDI collaboration. This is actually part of the Physics Beyond Collider process at CERN and this European strategy for particle physics update. Our idea is to have 2 scenarios with this machine. One, proton at 30 MeV, all electric, clockwise, counterclockwise beams operation, and protons at 45 MeV with additional vertical magnetic fields that would allow frozen spin. So there are some challenges which we think have to be met and which we defined actually. That means the all electric and the EB combined band operation. The storage time is an issue, clockwise, counterclockwise operation with very small orbit differences. The spin coherence time in such a purely electric ring polarimetry, magnetic moment effects, of course, you still have magnetic fields. And if it turns out that the spin coherence time is long, you have to think of actively cooling to really exploit that. I mean, if the spin coherence time turns out to be 10,000 seconds, you would want to have your beams survive 10,000 seconds. So we have to find a way to cool, and electron cooling is not a good idea because of the involved magnetic field. So you'd never get them under control. But stochastic cooling may be an option. So the point of this prototype ring here is to study the open issues and perform a first direct proton EDM measurement. Okay, that brings me to the summary here. So the search for charged hadron particle EDMs would actually open a new window to CP violation and may have some impact on the matter-antimatter asymmetry in the universe. We can search for static charged particle EDMs. Say protons, deuterons, helions could be there. I did not talk about an aspect of these experiments, which I think actually Ed will mention that in his talk, which is as soon as you have a sensitivity to an EDM, you can also have sensitivity to an oscillating EDM. And it's conceivable that actually there is a form of axion passing our universe, which could lead to, say, oscillating EDMs as well. And therefore, dark matter search is also an issue that, in principle, you can pursue with such an experiment. And we actually did a first experiment for an axion search, and I believe Ed will talk about this in some detail. So the present EDM experiment using the RF Wien filter is actually probably one of the last sophisticated experiments we do. COSY will stop end of 24. We had 2 runs, one in 18, one in 21, which was hard to run really with all the restrictions. We had many upgrades and improvements, and I showed you this pilot bunch that happened between run 1 and run 2. We think we get a sensitivity of about 10 to minus 20, maybe a bit better out, up to 10 to minus 20. There's a strong interest in these searches, in these EDM searches, as part of the physics program, say, of the post-LHC era. We are in this beyond collider process involved at CERN. Say the evolution of this yellow report is now that we just submitted a design study to the European Union to actually design that machine, which will take a couple of years to do the design, and then we would like to ask for funding to build this prototype ring. And this is actually site open. At the moment, we are considering CERN and COSI without COSI. I mean, IKP at Jülich, with the sources we have some expertise on there. So that could be an option. But in principle, I think where to put this prototype ring to do the next step is open. I mean, we can really think about anything. It shouldn't be that expensive. I think we have a price tag in the yellow report maybe of 15 million euro. So it's relatively inexpensive to start with. Of course, it's dedicated, and you need to find the resources for that. But I think it's the future. It's the future. Somebody on this planet will sooner or later do that, and we can as well be involved in that. Okay, thank you for your attention. And I hope I convinced you that we are really all standing on Willy's shoulders in a way. Many of these concepts were implanted in me when I interacted with him, when like others, like Ed was, he was also his PhD student, interacted with him. Erhard interacted with him a lot, and I had so much fun with him, and I do miss him. Thank you very much.
Thank you very much, Frank, for a very clear and engaging talk. And sorry about the technical details.
Ah, that's not a problem.
Question, Hans. I don't need the microphone. You do, because otherwise people don't hear you.
The others don't hear.
Okay, Frank. A polarized deuteron beam may carry tensor polarization. Can one just ignore that?
We have done these measurements with vector polarization only for time reasons. In principle, you can repeat the whole thing with tensor polarized beam. Not really, because the precession frequencies are different for the tensor. The precession frequencies are like twice as large for the tensor component. But I had the same question, actually. I had exactly the same question, and I asked Anatoly Zelenko to evaluate that, at least theoretically, and he came back with a negative answer. He said tensor polarization, even if it's there, it wouldn't contribute to this type of polarization buildup.
Frank, this is Thad Walker. Really beautiful, these storage rings. How do they scale for higher charges? Could you do this with highly charged ions, for example?
No, there we don't have a simulation, but it's conceivable that you do this with higher charged particles. I mean, we've been. Yeah, what are you thinking of? Uranium fully stripped, or what? What are you thinking of?
Well, you emphasized, taking smaller steps along the way, but there's a lot of work in atomic molecular EDMs on heavier nuclei.
Yeah, you need to have sources for that. So you need to have a source other than protons and deuterons and helions. That you have to do the whole spin gymnastics with the lithium beam or something in a ring, and there's just nobody does that currently.
well, people do make these, you know, electron beam ion traps with very highly charged, significant numbers of
Yeah,
highly
but I
charged
have not
ions.
seen that in such a storage ring environment.
No, that's my question.
Yeah,
Is
yeah,
there something-
okay, you can, I think you want, it's conceivable, but somehow this theory paper, which I cite there from Meissner and company, they basically say, if you want to get down to the quark EDMs, you need protons, deuterons, and helions to actually pin down the sources of CP violation. And sure, you could do it with the heavier charged ions, but the question is whether this really tells you much about the sources. So it's a physics question, what you are after, I think.
Why would you want to do heavier ions? I mean, if your questions are about the nuclear interactions within the nucleus, you don't learn anything by having bigger nuclei. If on the other hand, you want to learn scattering of larger ions, then of course you learn things, but why do you need a storage ring for that? Why don't you just use a tabletop experiment? Are you thinking about specific experiments? I'm excited about this. This is cool.
Well, I'm coming from the AMO community where the only possibility are the very heavy nuclei. And I kind of expected Frank's response there at the end that, okay, so you see an EDM in a mercury 199, you still got a lot of work to do. No question about that.
And actually the direct measurements is this a different story. As I showed you, all we know about the proton EDM is indirect from mercury, with lots of theory involved to get down to the elementary proton, if you want. And that's, I mean, for me, that's unsatisfactory. I would rather like to see a direct measurement.
So my interest is simply, trying to connect these, there's a lot of great work as you're describing with the light nuclei, people doing amazing things with the really heavy ones. Is there, somewhere in between that people ought to be looking as well? That's kind of the idea of the question.
Very good, thanks, yes.
Okay, thank you.
Ed Stevenson, I just wanted to try to answer Hans's really important question about tensor polarization. If you think about what is going on in the experiment, you're looking for the slow precession of the spin up out of the plane, and that produces a small vertical polarization component, which you detect by looking for a left-right asymmetry. If, on the other hand, you have some tensor polarization in the beam and the beam moves sideways, and this could be a failure of the feedback to put the spin directly along the velocity vector. So if you get out of that orientation, you also generate a left-right asymmetry. So this is a problem that needs to be addressed, and it has to be zeroed out in the experiment if you're using deuterons.
Yeah, it enters at some point. We have to consider this, but of course we have a polarization measurement from the source, so at least we know the injected, roughly the injected deuteron tensor polarizations, but we didn't really have the time in this experiment to do a careful measurement with tensor polarization. We didn't do that in this experiment. Also, I mean, we are losing the ability to do these experiments.
And maybe one single argument that kills this dead. You just have to find the argument.
Now, yeah, he explained it, but he analyzed the situation from a theoretical point of view, and theoretically one wouldn't expect that to enter. That's his statement. Of course, I keep this in mind, yes.
So this is Steve Vigdor. So when we were thinking about these experiments at Brookhaven, one of the qualitative concerns we had, and we never quite made it quantitative, is if you have a magnetic ring, like your prototype ring, You can get sequential rotations by going off axis through various magnetic fields, and those sequential rotations don't commute with one another. And you can mock up apparently time reversal violating effects that way. Have you done any estimates of what limits you get to because of that systematic effect?
Yeah, I mean, the point is that you have to measure the two orbits simultaneously, and you must make sure that both beams are on the same orbits. So that basically you have say you have a situation where you really have the effect twice, once with the clockwise and once with the counterclockwise beam. And in this scenario, if the two beams are exactly on the same orbit, these effects cancel.
If they're exactly on the same,
If they're
very high precision.
to a very high precision, absolutely, yeah. You have to have a lot of beam position monitors in the ring to be able to do that, and that's why I'm saying it's not simple. Actually, the prototype ring wouldn't be a primarily magnetic machine. It would be primarily an electrostatic machine, with the addition to have vertical magnetic field, so that one can have frozen spin for one beam alone in there as well, to test the frozen spin configuration. But at that point, you lose. I mean, with a magnetic field, you can't have clockwise, counterclockwise simultaneously.
Reason we talked about a purely electric ring.
Is that exactly? Is that? Yes, I see.
I had a question about your slide 30. If you can go back 10 slides, that beautiful sinusoidal curve, the zero curve underneath as a function of time, is it that an exponential decay or is it a linear? Why is it sloped down?
Yeah,
if it's linear?
it is sloped because as you go down here, the rates change in the detectors somehow. So this is an effect that
It's just a drift.
Yeah, it's basically a drift of the zero line of the polarization, if you want. You measure an up down. You measure, in this case, actually, it's really the vertical polarization. We started from the vertical polarization, and this effect here is basically a drift of the zero line of the asymmetry.
Excellent, thank you. Let's thank Frank again.
I think, yes.
And some coffee.